questions? Well, what we were talking about is displacements. And you can think of this as, the total displacement, the difference in the location before the loads are applied to after the loads are applied is equal to the displacement due to tension and compression plus the displacement due to thermal changes, temperature changes, plus the displacement due to torque. Plus the displacement due to the bending moment. And we talked about these two last time. These are both horizontal displacements. This one's a little more complicated to describe. I'll draw a picture to show you what that one does. And then the bending moment is a beam deflection, so that has to do with vertical changes. Okay. Before we start talking about displacements due to torque, here is a pretty common type of problem for elongation. So let's say that we have a relatively rigid bar and there's a force over here. And let's say that this bar is supported by a cable at the midpoint. And another cable, let's say at 0.6 meters away. And this whole thing is 1 meter. Okay, and we want to know what are the two cable tensions? Well, if you want to eyeball this and see to figure out whether this is statically determinate or statically indeterminate, notice that if we got rid of one of those cables, it would still be in static equilibrium until the cable broke, So the second cable just adds extra stability to this thing to keep it from collapsing, So this is going to be statically indeterminate. But of course, if you don't see that from looking at the picture, you can see it as soon as you do the statics because you won't have enough equations for the variables you have. So we're going to use the same approach we did before. We're going to do the statics, and then we're going to think about geometric constraints that will let us relate the variables that we've defined so far. And I said that this bar is relatively rigid. What I mean is that these cables are going to flex a lot more than that bar is. And so we're going to assume that that bar stays rigid for this calculation. Okay, and we're going to assume that those cables lengthen. And let me draw this just coming to the top here. Whoop. All right, so we're going to start with the statics. We have an unknown reaction force at the pin joint with the wall. I'll call that RA. We have the 5,000 Newton force here. I could have put a weight in here. Why don't I? So let's say that the mass of the bar is, that's 1 meter long. Let's say that it's 30 kilograms. So then there's going to be a weight force at the center of 30 times 9.81, 294.3. And then the only other forces are the two cable forces. I'll call that T1 and T2. So Newton's second law says RAX, RAY plus 0, negative 294.3 plus 0 T1 plus 0 T2 plus 0, negative 5,000. And this is static, so this is equal to 0. And you get RAX is equal to 0. And then the moment equation, I guess I'm going to use this as the about point. We have a counterclockwise moment of 0.5 T1, a clockwise moment of 0.5 times 294.3, so that is minus 196.2. No, it's not. 147.15. That makes more sense. And then the other T2, that's a counterclockwise moment of 0.6 T2. And then the 5,000, that's a clockwise moment. Moment arm is 1. So we have these two equations. The first one says T1 plus T2 plus RAY is equal to negative 4705.7. And the second equation says 0.5 T1 plus 0.6 T2 is equal to 5147.15. Yep.
Shouldn't we be adding the two constant ones together since they're both going down? Both equations.
Yeah, so that should be, yes, you are right. Thank you. So that should be positive 5294.3. Okay, now any questions? Well, can we solve this? No, we have two equations for 3 variables. So this is statically indeterminate.
So is it better to just leave RAX out of it?
I just already solved for it.
Is it gonna show up again at all, or?
No, we know it's 0. So we just calculated that from the x equation. That's the only x force.
Okay, and we won't need it in our reduced row echelon form later.
No, you can always, like anything you can solve for along the way, you can get rid of that equation and get rid of that variable.
Okay.
So we could think of this as, I mean, we could make a matrix, like think solving for this says that we got an equation, you know, a row in the matrix that has a 1 at the RAX position and a 0 in the constant position and nothing else, you know. So you can put it in like that or not put it in and it'll work either way.
Yeah, the only other thing would be is if we had a different equation where RAX appeared, we need to remember to substitute in 0.
Right, exactly.
Okay, show up again.
Right. Okay, so now we're here, statically indeterminate. So what are we going to do to come up with a constraint equation? Well, think of, so this is obviously very exaggerated, but this is the rigid bar after the deformation. Okay. This is, so if you think of the whole cable at the midpoint is something like that, right? And the whole cable at 0.6 meters away from the wall is like that. Before the deformation, they only come down to the red line. And so this is, okay, so this right here is the elongation. This is the elongation of cable 1, like this section that goes from the red line to the currently deformed position. And this one is the elongation of 2. Okay? And we know that this length is 0.5. And this length is 0.6. And notice that those are similar triangles. Okay? So we know that delta 1 over 0.5 is equal to delta 2 over 0.6. And so you can think of this as delta 2 is equal to 0.6 over 0.5 is 1.2 delta 1. Okay, so that's a geometric requirement. And now the problem is this introduced 2 totally new variables that we'd never talked about before. But now we can represent these elongations in terms of the cable tensions. Okay, so delta 1 is the internal tension in the cable times the length of that cable before the deformation divided by E1A1. We're going to assume that these cables have the same E and A. If they're different, you have to put those in differently. And delta 2 is 1.2 T1 L1 over EA. Well, actually, let me go back to step before and write this as T2 times L2 divided by EA. Okay. And then we can plug that into this equation to get, so we have T2 L2 over EA is equal to 1.2 T1 L1 over EA. And that is our fourth equation. We didn't introduce any new variables, so now we should be able to solve it. We can, since E and A are the same, we can cancel those. Since L1 and L2 before the deformation are the same, we can cancel those. And we just get that T2 is 1.2 T1. And so now you can plug that back into our system. So 0.5 T1, I'm going back to equation 2, plus 0.6 times 1.2 T1 is equal to 5147.15. And so that is 1.22 T1 is equal to 5147.15. And so T1 is 4218.98. T2 is 1.2 times that. And so T2 is 5,062.77. Any questions about that approach? Okay. Well, notice that just from the geometry, you can see that as this thing tilts down, the farther away you get from that hinge, the more force that cable is going to have to support, or well, the more stretch it's going to have. If they're different materials, then it might be it's more complicated figuring out what the forces are. I mean, just off the top of your head, guessing what the forces are going to be in relation to each other. But you're always going to have more elongation as you get farther away from the hinge. Yes?
The elongation always increases linearly because of this triangles.
Yes, exactly.
And this is not a perfect world because there's a little bit of deformation on the
right, but we're assuming that
small.
Right, we're assuming that the elongation in the cables is a lot bigger than the deformation of the beam, right? So if you set up a problem like this, like for designing a setup like this, if you set it up with one cable all the way at the end here and one cable right here, and they're basically the same cable, same cross-sectional area and everything, what would you expect to happen with those forces? The force here would be tiny because it's not elongating very much. And the force here would be supporting almost all of the weight or the other forces. Yep.
So we don't know anything about the actual distance moved in this example?
Oh, well, we could calculate it now. I just calculated the things we're looking for, but we have the expressions right here. So now that we have T, we could figure that out. Well, I didn't give us E and A and stuff, but if those were given, we could. And like you would expect, if this ceiling is 50 meters above the beam, then it's going to stretch a lot. And if those cables have big cross-sectional areas and big stiffnesses, then that's going to limit its stretching. It's not going to stretch very much. Let's do this one more time. But this time, let's say cable 1 is steel. And cable 2 is copper. So that's about 110 times 10 to the 9. We're going to assume that the cross-sectional areas are still the same. Okay, so what's going to change in here? We didn't use any of those material properties in the statics, right? The statics never care about that stuff. When in statics, I never even brought up material properties. So these equations are still good. Okay, so we still get the same two equations from Newton's laws. So I'll copy these. But now for the elongations, we know that, so this was geometry. So we know that delta 2 still has to equal 1.2 delta 1. Okay, that doesn't have anything to do with the materials. But now when we get into the definitions of these things, our delta 1 is the tension in 1 times the length that they both share, divided by 200 times 10 to the 9 times the cross-sectional area. And delta 2 is T2 times L divided by 110 times 10 to the 9 times the cross-sectional area. And now we'll plug these into the geometric relationship. So we have T2 times L divided by 110 times 10 to the 9 times A. And that's equal to 1.2 times T1 times L divided by 200 times 10 to the 9 times A. Some stuff still cancels, but the Young's modulus don't cancel. The A's cancel, the L's are the same. I'll cancel the times 10 to the 9. And so we get 200, I'm just cross multiplying, 200 T1, T2 is equal to 1.2 times 110 T1. And so T2 is equal to 0.66 T1. Remember in the first example, when they were the same material, we got that T2 is equal to 1.2 T1. This time, since it's a weaker material, even though it's farther out, we're going to see that the tension in that copper cable is smaller than in T1. So now you can take this back to the equation 2. You get 0.5 T1 plus 0.6 times 0.66 T1 is equal to 5147.15. And you get 0.896 T1 is equal to 5147.15. So T1 is 5744.98. And T2 is 3791.69. So when those two were the same materials, we had the higher tension in the cable that was farther away from the hinge. Okay. When the stiffer material, the steel, was closer to the hinge, we got that the steel cable is supporting more of the load than the copper cable. Yes?
You say from hinge, if the force was on the inside of the first cable, then we'd expect the first cable to have higher tension in both cases, even though it's near the hinge.
Okay, so if you're saying if it was set up like this and the cables are here and the force is here. No, really all that does is these two cables are both supporting a moment, a total moment, and all this does is reduce the total moment that they're supporting. The relationships between those two tensions or the deformed length of those two cables would still be the same.
So the one on the outside would still deform.
Yeah, the one on the outside still deforms more because this applied force, even though it has a smaller moment arm, its effect is still just making that triangle appear, and you're still just dealing with the similar triangles. Any other questions about that?
Kind of backwards from what you think.
Oh, yeah, like you'd think the weaker thing is supporting.
No, in my mind, I picture that the cable closer to the bottom of the beat.
Uh-huh.
Still, but you're right.
Right. Well, what you, I guess, maybe connected to what you're thinking there is if you only did these one at a time,
Yeah,
this would have to pull harder
yeah,
than this would, you know? But the geometry says that this, as you get farther away from the hinge, it stretches more. So the question is just, for the given cable geometry and stiffness, how much tension does it take to stretch that required amount?
Or if the beam wasn't rigid, you could see like a U shape.
Yeah, that's right. Yep. And once we talk about beam deflection, you could do a problem where you took into account the deflection of the beam and took those in, but you'll see that it would get really, really complicated. I mean, not that complicated, but surprisingly complicated. Any other questions? Okay, so now we're going on to maybe the easiest of all of these. That's angle of twist in the presence of a torque. Okay, so I'm going to draw a pretty thick, relatively short bar that's in torsion. And we're going to imagine there's a couple this way on that end and a couple this way on the other end. And the effect of that is going to be, so there's a torque this way on that side and this way on that side. And let's say that there's a line drawn on this thing like this. Okay? Before you apply those torques. What? Yeah, you could think of a seam, yeah. But all we care about is that we're tracking what those points do once we apply the torques. Okay? And what those points are going to do is they're going to develop an angle like that. Okay? I keep missing. Okay. I'm going to erase these. And this angle here, I'm going to call that phi. That's the angle of twist. Okay. Can you picture what I'm drawing there? And does that make sense? So over the length of that piece, there's a total angle phi. There's an integral definition for this, but there's really never any reason to use the integral definition. So I'm going to give it to you, and then I'm just going to emphasize the summation, the finite formula for this. That's the one we're going to use. So the integral definition, that's not useful except for defining the other one, says that the angle of twist is equal to the integral over the length of the bar of t dx over g I sub p. Where g is e over 2 times 1 plus nu. Have you ever seen that G before? You have. Can you think of why that looks familiar? If you think of the shear element of the compliance matrix, it's the reciprocal of that. And so you can think of, well, this is the shear element of the stiffness matrix, or, this is the shear element of the compliance matrix is 1 over this G. Okay, so you can think of that as like the shear version of the stiffness. Okay. The formula that we're going to use is just when these are piecewise constant. Like, we're never going to have a case where any of these variables are varying continuously. And so what you get is that the angle of twist is the sum over all the pieces. Say there's a total of capital N pieces of T times L over G IP. G IP, freely. Notice the similarity to the elongation formula. This will help you remember it. So you can always think of these as the load times the length of the piece divided by the stiffness times the geometric resistance to deformation. Okay. So if you're talking about the elongation formula, the load is the internal tension times the length. The stiffness is E, and the geometric resistance to deformation is just the area, the cross-sectional area. In this case, the load is the torque length, the stiffness is that G, and the geometric resistance to deformation is the polar moment of inertia. Okay? So let's say first we'll do like a cantilever thing, and let's say we have a torque in the middle of 200 Newton meters, and then a torque at the end of 300 Newton meters. The whole length is 1 meter. And we'll use a G of 80 times 10 to the 9th. And a polar moment of inertia of 1.57 times 10 to the minus 8th. This is meters to the 4th. And we want to calculate the total angle of twist. Well, first we have to figure out what that external torque is. So we have 300 here, 200 here. This is our reaction torque at the wall. So the x component of the moment equation says TR plus 200 plus 300 is equal to 0. So TR is equal to negative 500. And now we can think of the cuts. Cut 1 is for the first half of that bar, 0.5. And so you can see that, I guess I'll write out the equation, but you can see that T is going to be equal to positive 500. And then for cut 2, for x values between 0.5 and 1, now you have the 500 this way, the 200 this way, and so the moment equation about x says negative 500 plus 200 plus torque is equal to 0. And so that internal torque is 300. So now the angle of twist is equal to, this first piece is 500. The torque is 500. The length is 0.5. The G is 80 times 10 to the 9. The polar moment of inertia is 1.57 times 10 to the minus 8. The other one is 300. The length is 0.5. We divide by 80 times 10 to the 9. 1.57 times 10 to the minus 8. And I got an answer of 0.318, and this is in radians. Any questions about that? Remember that the signs matter. So if I would have gotten on this second half, if I would have gotten a torque of negative 300, you have to consider that. Okay. And this angle of twist that you get is, you know, it has a direction. Like that is a positive angle of twist. Okay. What about using this in statically indeterminate structures? I'll just do a real simple one of these. So let's say we have a wall over here and a wall here. And at the middle, a torque is applied of 500 Newton meters. Okay. And again, let's say this thing is 1 meter. And let's use those same properties. So G is equal to 80 times 10 to the 9. Polar moment of inertia is 1.57 times 10 to the minus 8. Okay, well, and what we're trying to find here are the external loads, or what are the external torques. Well, first we'll do the statics. Doing this step is how you figure out for sure whether it's statically indeterminate or not. So free body diagram, we have a reaction torque here. I'll call this torque A. And a reaction torque here, call this torque B. And then we have this 500 Newton meters. And so the moment equation says torque A plus torque B is equal to negative 500. That's one equation for two variables, so now we know it's statically indeterminate. So we can't solve this, but we can express the total angle of twist in terms of TA and TB. So our cut 1 is for x's from 0 to 0.5. So we have our torque A over here, our internal torque there. The moment equation says TA plus internal torque is equal to 0. So the internal torque is equal to negative TA. And then cut 2 for x's between 0.5 and 1. There's torque A. This time we also have the 500. The moment equation says, this is TA. The moment equation says TA plus T is equal to negative 500. So the internal torque is negative 500 minus TA. Okay, so now the total angle of twist is the angle of twist from the first piece, that's negative TA times 0.5 divided by G I sub P. I'll just leave those like this because they're all going to cancel, we'll see. Plus the angle of twist from the second part, which is negative 500 minus TA times 0.5 divided by G I sub P. And if these two things are locked between two fixed walls, what's the total angle of twist over the length of this thing? 0. Yep, the two ends can't go anywhere. So there would be an angle of twist in the middle somewhere, you know, but then by the end it has to be back at its original position. And so this is equal to 0. Now we can cancel that stuff, and we get that negative TA minus 500 minus TA is equal to 0. And so TA is equal to negative 250. Now you can plug back in and use the static equation to solve for TB. So TB, these have to add up to minus 500, so this also has to be negative 250. So in this case, because that torque was exactly in the middle of the bar, it splits those two torques evenly. But if it was closer to 1, you'd have a bigger torque in the one it was closer to. Any questions about that? Okay, that's all.
Oh, yeah, what about the,